Welcome back, Pre-Calc Excel students. Today we're going to begin section 10.7, but we're going to start off with a warm-up from 10.6. So with this warm-up, what I'd like you to do is find two sets of parametric equations with opposite orientation for y equal to 2 minus x. Okay, so here's your rectangular equation. You want to come up with the parametric equations, and you want two sets so that they have opposite orientation. So pause the video, give it a try, and then come back and we'll compare solutions. And remember, there's infinitely many possibilities here, but try to keep it simple. Okay, go ahead and give it a shot. Okay, let's see how you did. So keeping it simple, I let one set of equations be x equal to t, which makes y equal to 2 minus t. For the second set, I let x equal negative t, which makes y equal to 2 plus t. So if you look at some coordinates, I just randomly picked points from negative 2 to 2. You can see how you end up with the exact same coordinates, but when you look at increasing order of t, they're going to be plotted in an opposite order, which makes that orientation opposite. Okay, let's move on to, we have a second warm-up for this section, just to refresh your memory on some of your other trig function values. So go ahead and give these a try, pause the video, and come back when you're done. Okay, let's see how you did. Go ahead and compare answers. Takes a little bit to get those gears turning sometimes, right? All right, so let's begin the section. 10.7 on polar coordinates. A polar curve is a shape constructed using the polar coordinate system. Polar curves are defined by points that are a variable distance from the origin, which we call the pole, that would be the center here, depending on the angle measured off the positive axis. This is called the polar axis. So this is a polar grid made up of concentric circles, and this is what we'll be plotting our points on. So if you put the rectangular grid over top of this, your coordinates would be in the same position. Okay, so it's just a different type of grid and a different way to graph the points. Okay, so there's no longer an x-axis or a y-axis or an origin, and we call this the pole. This is the positive x-axis. All this is on another page, and the vertical axis would be the line theta equals pi over 2. So polar curves can describe familiar Cartesian shapes such as ellipses, as well as some unfamiliar shapes such as cardioids excuse me, and lemniscates. So whereas Cartesian curves are useful to describe patterns in terms of horizontal and vertical distances, polar curves are more useful to describe the paths which are an absolute distance from a certain point. One practical use of polar curves is to describe directional microphone pickup patterns. A directional microphone will pick up different qualities of sound depending on what location the sound comes from outside the microphone. For example, a cardioid microphone has a pickup pattern in the shape of a cardioid, and that's the shape that you see right here. So there are lots of applications to this. It's kind of cool stuff, something different. So here again is a picture of the axes. So this is the polar axis. This is the pole. And this line you could call theta equals pi over 2. So our points in polar form have the form r comma theta. R would be the distance away from the pole, the directed distance from O to P. Theta is the direction angle from the polar axis to OP. And we always go in a counterclockwise direction, just like we have in the past with the unit circle. So rectangular coordinates are unique. This is not the case for polar coordinates. So r theta could also be written as r theta plus or minus 2 pi n, where that 2 pi n added or subtracted to theta gives us an angle coterminal to theta. So there's lots of different possibilities to come up with polar coordinates. We can also use a negative r value for the first coordinate. In that case, theta would be plus or minus. This is the form for an odd number, right? 2n plus 1. So theta plus or minus an odd multiple of pi would be used. And this is, of course, when n is an element of z. Remember, z is the integers, the set of integers. The pole is represented by any coordinate that is 0, theta, and theta is any angle. Because if r is 0, that means you're not leaving the pole. Okay, so let's try plotting some points. We're going to plot these points, and then we're going to find 2 additional polar representations of that point. So our first coordinate is 3 negative pi over 3. So that means I'm going 3 radii out to the right, and then I'm rotating in a negative direction. So I'm going negative pi over 3. So here's point A right here. So another name for this point, I could go 3 radii to the right, and then I could rotate in the positive direction, and that angle would be 5 pi over 3. I could also use negative r, which means I go out to the left 3 radii, and then I could rotate around in a positive direction, and my angle would be 2 pi over 3. So again, lots of possibilities because you can keep going around the circle in either direction, either starting from a positive r, which is 3 to the right, or a negative r, which is 3 to the left. So go ahead and try B and C, plot the points, find 2 additional polar representations of that point, and then come back and we'll compare solutions. Okay, so for B, we're going 2 to the right, and we're rotating to pi over 6. So here's point B. And then I'm going to just plot C before actually let's look at the representations. So let's see what I chose to do. So for one point, I went 2 to the right, and then I rotated in the negative direction, which would be negative 11 pi over 6. I can also go to the left and rotate in a negative direction, and that would be negative 5 pi over 6. For C, I'm going to go negative 1 to the left, and then rotate positive pi over 4, so that puts the point right about here. And by the way, I added some grid paper to your note packet if you want to print that off and use it. There's 2 different types of paper. This grid there's another grid that has more angles, more lines going through it to give you a better selection, I guess I'd say, for the angles in between 30 and 60. Okay, so let's look at the polar representations. So I went in the positive direction 1 radius and then rotated in a positive direction counterclockwise around to 5 pi over 4. I also went in the positive direction of r and rotated negative 3 pi over 4. So those are 2 possibilities. Now, when we learn how to plot points, let me show you something from Desmos. Once you know how to plot those points, we'll be plotting them and coming up with some pretty cool grids. I don't know why this is acting freaky. I wasn't doing this before, but it was sketching out our butterfly shape pretty nicely. I wanted you guys to see that. That's disappointing. I'm not sure if it's because I'm on the video or not, but if you're interested in seeing it, it was pretty cool. It sketched it out, and you could see how the points were plotted going around the pole numerous times to get the polar fly. But you could go to Desmos and look up polar graphs if you're interested in seeing it sketched out. But there's some cool stuff ahead in the next section. Okay, so let's move on to coordinate conversions. So these are the equations that we'll be using to convert coordinates and equations, okay, later in this section. So polar form, the form is r theta. For rectangular form, the points of the form x comma y. So we're going to use, for sine of theta, we know that's y over r. Cosine theta, x over r. And tangent is y over x. Right? That's all from our trig definitions. So to go from polar to rectangular, we want to change it to x and y. So we're going to use the fact that x is equal to r cosine theta, and that y is equal to r sine theta. If we're going from rectangular to polar, then we need theta and r. So we're going to get theta by using the fact that the tangent of theta is equal to y over x, and we're going to get r from this equation, that r squared is equal to x squared plus y squared. So these are all, should all be familiar equations from things that we've used in the past. So to convert this point, this is in polar form, right? 4 comma pi over 2. I need x and I need y. So x again is r cosine theta, which in this case is 4 cosine pi over 2. The cosine of pi over 2 is 0, so that coordinate is 0. For y, it's going to be 4 sine pi over 2. The sine of pi over 2 is 1, so we end up with 4. So in rectangular form, the point would be 0, 4, which should make sense because if you think about the location of this point, we're going 4 radii out, and then we're rotating to pi over 2, which is directly above the pole. And if we put the rectangular grid on top of the polar grid, 0, 4 would also be right above the origin, right? 4 units out, or 4 radii above the pole. Okay, so to convert to polar, so these are our xy coordinates, right? So we need r. Remember, r is the square root of x squared plus y squared. So that gives us the square root of 8, and we want to reduce that to 2 root 2. And theta is equal to the tangent inverse of 2 over 2, or the tangent inverse of 1, which we know is pi over 4. So again, if you think about it, 2, 2 is right through the middle of the first quadrant, and so is pi over 4. Right? We're rotating pi over 4, and we're going 2 root 2 radii away from the pole. So we're going out to the right to root 2 and rotating pi over 4, which would put us at the same location as 2, 2. So some of these if you recognize where the point is, you don't really need to do the work. Right? A lot of them you could just figure out just by knowing the location of the coordinate. So go ahead and try the B examples, pause the video, and when you're done, come back and we'll compare solutions. Okay, so for 2 pi over 6, now we're going to rectangular. So x is equal to 2 cosine pi over 6 and 2 sine pi over 6. So hopefully you ended up with the coordinate root 3, 1. For -1, 0, now this is rectangular. We're going to polar. So we're taking the tangent inverse of 0, which is 0, and r is equal to 1. So there's different possibilities here. We could use 1, pi, okay, or we could use -1 and 0. So when you think about it, this polar coordinate looks exactly the same as the rectangular coordinate. So you might be saying, well, how do I know which one it is? Is it the polar or is it the rectangular? Usually in the context of what you would be doing, it would be clear that this is a rectangular coordinate or this is a polar coordinate. But again, this is just to emphasize there's lots of different choices. -1, 0 is at the same location as 1, pi. And then there's infinitely many more choices. So that's where we're going to stop the lesson at this point. Tomorrow, or not tomorrow, but the next lesson, we'll pick up on converting equations, which can be lots of fun as well. So I hope you enjoyed this lesson. Again, if you want to go and see that cool sketch of the butterfly, you can go to Desmos and look up polar graphs. I found it pretty easily, but it's pretty cool stuff. So have a good day, and I'll see you next lesson.